Hello. In this video, we're going to take a look at a couple of applications involving quadratic equations, maximizing and minimizing, using some fencing problems. So these are kind of some classic quadratic function applications. All right, so we have a rancher that has 520 yards of fencing with which to enclose a rectangular pen. First thing we need to do is express the area of the pen as a function of its width. So let's draw a picture to kind of see what it is that we're talking about here. So this rancher is going to fence off a rectangular pen for some particular purpose and has a total of 520 yards of fencing with which to do this. So if we let W be our width, well, that's going to be the length on the bottom and on the top, and then we'll let L be the length or the height, whatever we want to talk about. It looks like a height on my paper, but I'll call it a length. If we have 520 yards of fencing, we want to write this as a function of the width. So that means we need to get rid of those L's. Well, if we use W yards of fencing to do the top and the bottom, that means what's left is going to be split in two to do our two lengths. So that means that our L is going to be 520 minus the 2 times W that it's going to take to do the top and the bottom, and then we got to split that in two to get our length. And the good news is this one simplifies quite well. 520 divided by 2 is 260, and 2W divided by 2 is going to give us a W. So our area is going to be length times width. Well, we just said our length is going to be 260 minus W times our width of W. Let's go ahead and distribute that W, and we get 260W minus W squared. And then I'm just going to go ahead and rearrange this and write that squared term at first. So negative W squared plus 260W is our area function. So that would be our answer for part A. Now part B wants us to find the width with which the area is maximized. Well, remember, quadratic equations will be maximized only if they open down, and then that maximum value will occur at the vertex. And we do see that our leading coefficient here is a -1, and so it is going to open down. So we will actually have a maximum here, and that maximum will occur at the vertex. And the width at the vertex, the width here is our independent variable, so that's going to be at -b over 2a, where b is our coefficient on W, so we get -260 over 2 times our a value, which is -1, and -260 divided by 2 times -1, the negatives are going to divide out. 260 divided by 2 is 130, and the units on this are going to be in yards. So 130 yards is going to give us that maximum area, 130 yards on our width, and then we'll plug that back in to find out exactly, what our maximum area is going to be. So we'll get -130 squared plus 260 times 130. Now remember, the 130 is the part that's squared, that negative is not. So -130 squared plus 260 times 130 gives us a maximum area of 16,900 square yards will be that maximum area. All right, let's look at another one that's a similar setup, but we've got just one little change here. Here we have a farmer that has 500 meters of fencing to enclose a rectangular plot, but this one's next to a barn, and there is no need to fence the side along the barn. So one minor change here. So we've got our barn, and we're going to fence. So we'll do our width and our length, but we don't have to worry about fencing along the side of the barn. And so instead of having up here, we had that our length was our total minus 2 times W. Well, this one, we've only got to fence one length of W. So our length here is going to be, we've got a total of 5,000 feet of fencing, but we only have to subtract out 1 W. Still need to split it across 2, so we're still going to divide by 2. So that's going to be 2,500 minus 1/2 W. But other than that, the problem works exactly the same. We're going to do those same 3 steps. We're going to find our area function. So our area is going to be 2,500 minus 1/2 W times W. Distribute that W. I'm going to go ahead and simplify this and distribute and write it in standard form. So I'm going to distribute to that second term. So we'll get negative 1/2 W times W is negative 1/2 W squared. And then we get plus 2,500 W. So that'll be our area function. Again, it opens down. We've got a negative coefficient on our W squared. It's going to be maximized when W equals negative B over 2A. Our B here is 2,500 over 2 times negative 1/2. That denominator is going to simplify to negative 1. So we're going to get that our width that gives us that maximum area is 2,500. And then if we plug that back in, negative 1/2 times 2,500 squared plus 2,500 times 2,500 is going to be let's see, that's going to be a 3,125,000 square meters is going to be the area of our pen in this scenario. So that better be a pretty long barn in order to get that maximum area. All right, I'll see you guys next time.